Hey, hello everybody. Actually now we are going to talk about the last topic in our class. Before we get started, let's review what we've already learned in the previous class. What have we learned in the previous class? So it is actually friction for particles, right? It is the frictions for particles. Why it is a particle? If we go back to the problems that we had in the previous class, for objects, for box, we never talk about what? We never talk about the dimension of the object, right? Therefore, we can simplify that into particle. Then how many equations do we have? So actually, if you go back to the examples, for each of the example, we only have for an object, we only have two equations: summation forces along x, summation forces along y, both equals to 0, right? Okay, so that is actually corresponding to equilibrium of a particle. And the in addition to typical equilibrium particle, so we have a friction coming, right? Okay. Sometimes we know that in our life. So actually, in our real life example, so there's some examples we have to consider the dimension because the dimension of the object cannot be ignored, and sometimes it is important. Sometimes it can really influence the actually the result of our analysis. Okay. For example, here. When you have an object, okay, now I'm going to give an example here. So now we have object here, okay. So now if I apply a force on it, so what kind of consequence can you expect? For example, consequence one here is that it will not move if your force, the magnitude of force is not big enough, right? Okay, so consequence two is that if I apply force, it may be able to slide, right? Okay, so if the map of if the magnitude of my force exceeded what? Exceeded the limiting static friction, right? It is a maximum friction that my surface can provide. And thirdly, if I have the line of action of my force is kind of high, then what would happen? It will actually tip over, right? It will actually tip. So now actually we see that sometimes the line of action of my force can influence the behavior and consequence. So that cannot be well represented by particle models here. Okay, so we are going to talk about it. So the topic for this class is so it is lecture 24 here. Slippery and tapering. Okay, so in other words, we can see that it is a friction for for general rigid body. Okay, okay. So now I'm going to directly start from an example and see how we can analyze it because we've already see a real example, right? When we change the line of action of the force, so sometimes it will directly slide. So that actually corresponds to translational motion here. But sometimes it will tip, right? It will overturn. So okay, given given that I have an object here, okay, and it is located on ground, okay, or a surface. And suppose that I know the dimension of an object here. I have the width to be 4 feet here, and the head is 8 feet. Okay, and I have the coefficient. I have the coefficient of the static friction here to be 0.4. Okay, so it is our mu s here for the contacting surface. Okay, so now if I apply a force here of 30 pounds, okay, and we describe the location of a line of action as the distance from the line of action to ground, which is h. Okay. And suppose we also know that the weight of the object is 100 pounds. Okay. So now you are supposed to find. You're supposed to find. First, it is a maximum. It is a maximum height, h, where the 30-pound force can be applied. And the box does not hit. Okay. In other words, we are going to find out the maximum height such that such that the box or the object will not overturn. Okay. And secondly, does the box split? Okay. So actually here's our question 1, and here's our question 2 is that it is asking about if the box will start to slip. Okay, so how can we approach that? Again, so as we've been talking about, and go back to talk about friction, it is another topic of force analysis, right? Then again, what is the first step for force analysis here? Okay, so it is a free body diagram, right? It is a free body diagram here. Okay, so the first step here is to draw free body diagram. Okay, so now for the free body diagram, we know that it is composed of what? It is composed of the object that we're going to analyze and all forces on it, right? Okay, first we have the object that we're going to analyze, and clearly for this example, it will be the box, right? So we're going to analyze the box here, okay? And we're going to draw the we are going to draw the box here. Okay, so for the box here, and we know that for free body diagram, it is also have what? It will also have all forces on it, right? Because the free body diagram is the tool that we are doing force analysis, right? It is going to have all forces on it. So what forces do you think that we have on the object here? Okay. Okay. So first, we have the weight, right? Therefore, the object is subjected to gravity force, right? The object will subjected to gravity force, and for the use of visualization, we draw the gravity force towards the center of gravity or center of mass here. Okay, so we know the magnitude equals to, we already know that it is actually 100 pounds, right? It is actually 100 pounds. Okay. So in addition to that, what else do we have on the box here? We know that the box is subjected to external force, right? It is subjected to external force here, which is 30 pounds, right? Which is 30 pounds here. Okay. And do we know the line of action? Okay. So we know that the line of action is specified by what? By h. It is the distance from the line of action to the ground, right? Okay, in addition to that, what else do you think we have here? Normal, right? We should have normal for first here. Okay, now here's the thing. Do we know the direction of the normal do we know the direction of the normal force here? So so as indicated by the name, right? So the normal force is normal to what? It's normal to the contacting surface, right? So given that the contacting surface is horizontal, then the normal force should be vertical here, right? And going up, right? Okay, now here is a tricky thing. Where do you think is the line of action of my normal force? Where do you think is the line of action of my normal force here? Right? Okay. So now, typically, as we know that the line of action of normal force should be at the very middle of my contacting surface, right? Okay. But now, where is my contacting surface here? Okay. So it appears to be the entire bottom surface here, right? But actually, we are considering a state of what? A limiting state here, right? So we are considering when the box is going to tip, but has not yet tipped. So actually, we are trying to consider the critical status that the box is going to tip, but has not yet tipped. And exactly at the moment when the box is going to tip, where is the contacting surface point here? Okay, so as we know that if we have object and it is going to tip, it will start to rotate about a corner, right? Okay, and the entire surface will what? So when it starts to tip, the entire surface will be actually detached from the contacting surface, right? So there will be only a corner. There will be only a corner contacted to the surface. So the contacted surface or point of the object will be only the corner here, right? It will be only the corner here. Then where is the line of action of my normal force here? So it will be crossing the point, right? So my normal force is actually here. This is very important, okay? Because only when we have this kind of distance between the line of action of normal force and the gravity force, they will form a couple that's balance out the overturning couple that caused by the external force here. Okay. Okay, so now we've already have the normal force, we have the two external, actually we have an external force and the gravity here. So in addition to the three forces, what else do we have here? We also have, as indicated by the topic, right? We are also going to have a friction here, right? Okay, where do you think is so what do you think is a lab action of the friction here? So typically it is along the conducting surface, right? Okay. So do you think it is going towards the left? Do you think it is going towards the left or right here? Okay, so typically the friction is trying to what? It's trying to stop relative motion between the object and the surface, right? Therefore, it will go against to the tendency of motion. Now, where is the tendency of motion? It is actually the same as my external force. It is going towards the right. Therefore, my friction is trying to cancel that. It is actually going towards the left, right? It is actually going towards the left here. Okay, this is actually our friction here. Okay, so now, is that all we have here? Okay, so now actually it is all the forces that we have on the object. Okay, so typically for force analysis for all objects in the chapter friction here. So typically the free body diagram should contain external force, gravity, normal force, and friction. Okay, typically it's the four forces that we have, and based on this idea, you can check if you have already included all forces on your free body diagram here. Okay, so now we already have all forces here. Now we can go ahead and analyze it. Okay, so then what is the next step here? It is to establish equations, right? It is to establish equations. So it is the equations of equilibrium. It is the equations of equilibrium here. Okay. How many equations do you think we have for the object here? Since it is a rigid, so now it is a general rigid body here, so it will have three equations, right? Summation of forces along x direction equals 0, summation of forces along y direction equals 0, and summation of moments about a point. Okay, so essentially it has the three equations. Of course, if you establish all the three equations, definitely you are going to find that it can solve the problem. But here actually, since that we are actually only concerned about, so we are trying to solve the first problem here, okay? So the first problem is only concerning about what? Concerning about tip here. So tip is, so tapering is also sometimes we can call it overturning. It is what kind of motion here? It is actually rotation, right? It is actually a rotation about the corner here, right? Okay. What equation do you think is related to rotation here? It is actually equation of equilibrium of moment here, right? It is equilibrium of moment here. In other words, it is summation of moment about a point equals to 0 here. Okay, so now actually to solve the first problem here, only the equation of equilibrium of the moment, it is enough. Okay, so now we're going to establish equation here. So it is summation of moment about a point equals to 0. Okay, summation of moment about a point equals to 0 here. Now about which point, so are you going to take the summation of moment here? Okay, so now you can pause the video here and think about that for 1 minute here. Okay, so now we will come back. And actually, here, if I see the corner here is A. Okay, so if we take the summation of moment about A, then, okay, we see that there are actually two unknown forces here, but all the line of action of the unknown friction and unknown normal force, they cross what? They actually cross my point A. Then will they contribute to the summation of moment here? No, right? So there will be, since their line of action all cross A, their contribution to moment about A actually equals to 0, then both of unknowns will actually not appear in my equation, right? So it seems a good idea to take summation moment at A here. Okay. So now if we take the summation moment at A, what should we have? What forces do you think will contribute to the summation moment at A? So first we have external force here, right? So the moment of my external force with respect to A equals to the magnitude. Okay, so the magnitude of my external force times what? Times the distance between the line of action of my external force to A, which equals to actually the head, which equals to the head of my line of action of my external force, right? And it is the unknown that's of our interest, right? It is actually H here. Okay. Okay, so I'm going to denote it here. So it is actually the distance from my line of action of my external force to A, right? We assume that it is H. Okay. Now, given that typically we assume that counterclockwise is positive here. So do you think so what do you think is the sign of the moment here? It is a positive or a negative here. Okay. So now we see that actually if we have our pin here and we have one end of our pin fixed at A and we push it along the direction of the external force actually is rotating. It is rotating counterclockwise or it is actually rotating counterclockwise or clockwise here. It is clockwise, meaning that it is negative here. Okay. Okay. I'm going to separate that too. Okay. So that is actually the moment of my external force above A. In addition to that, what else do you think will contribute to the moment of contribute to summation of moment at A? That actually is the moment of my gravity here, right? Okay. So it equals to the magnitude of the magnitude of gravity here, right? So the magnitude of gravity here, which is 100 pounds. Okay, times what? Times the distance between the line of action of my gravity force to what? To A, the point about which we are actually calculating the summation motion here, right? And it equals to, since we know that line of action of my gravitational force cross what? Cross the center of mass or center of gravity, right? Okay, so actually it's so the distance from my line of action to A equals to what? Equals to a half of the actually it is a half of the width of the object here, right? Which equals to 2, right? It is actually 2 here. Given that the total width is 4 and a half of that is 2 here. Okay. Now positive or negative here. Okay. So again, we have our pin fixed here, and if we with one end fixed at A, and another end if we push it along the direction of the direction of force, we see that it is rotating clockwise or counterclockwise here. It is actually rotating counterclockwise, right? So it is positive here, right? Okay, it is a positive here. Okay, and that equals to what? Summation of all moments equals to 0, right? Okay, it is the equation that we have. So now if you look at the equation here, it is actually composed of two. It is actually composed of two terms or two moments here, right? And they are canceling each other out. So the first term here. Okay, so the first term here is actually the moment that it is actually the moment of my external force and causing overturning. So that is actually the term that's causing overturning. Okay. And the second term here. Okay, so the second term is actually the moment of my self weight, right? It is the moment that keep the object to stand there and keep it from taper, right? Okay, so when the overturning moment exceeded the moment of gravity, it will what? It will actually tip over, right? Okay, so when the overturning moment is smaller than my that moment of my weight, it will what? It will stand still, right? Okay, so and at the very critical point when the object is going to overturn, so we have this equation of equilibrium for that critical status. Okay, so if we solve that, if we solve the equation, so there are only one unknown here. We're gonna have h equals to, okay. So h equals to 0. Sorry, so it is a 6.67 feet here. Okay, that is the answer. Okay, So it is essentially saying that if we increase the height here for a little bit, that means my overturning. So actually, it's the magnitude of my overturning moment will exceed the moment of my weight. Then the object will start to overturn, tapering. Okay, okay. So now we've already solved the first question here. Okay, it is this is the maximum height that we can have to have the object to stand still. Okay, so to have the object that does not tip. So now if we go to the second problem here, and how can we approach that? Okay, so actually for the second problem here, it is a kind of problem that we've already addressed in the previous class, right? So to check whether the friction that I need exceeded the maximum friction that my surface can provide, right? Okay, so now we come to the second problem here. Okay, so now what is the maximum friction that my surface can provide here? According to what we learned in the previous class, it equals to okay. So it is equals to the constant of static friction here, and which is actually mu s times what? Times the magnitude of normal force here. Okay, right? Okay. Okay. So now, and what is the magnitude of the friction that we need to keep it from slipping? Okay, to analyze that, we have to establish the equation, right? Okay, before we establish the equation, actually we should have the free body diagram, and we were already have here, and we can directly list the equations that we have. And now it is time that to establish equations. The equations actually summation of forces along x direction equals 0, summation of forces along y direction equals 0, right? Okay. So now, by summation of forces along x direction equals 0, and what do we have? What do we have along x direction here? So we have external force here, right? This is 30 pound. Okay, positive or negative here. Since it's going towards the right? So we assume that the right is positive, so it is positive here. And what else do you think is actually we should consider here in the summation of forces on x direction? Friction here, right? It's the friction here is also a horizontal force here, right? Okay, so we have a friction here. Positive or negative here. Okay, so given that it's trying to cancel out my external force, it is negative, right? Equals 0. Okay. So we also have summation of forces along y direction equals 0. Right? Okay. What do we have along y direction here? First, we have the gravitational force, right? So it is a 100 pound. Positive or negative here? Okay, since the gravitational force is going downward, so it is a negative here. Okay. Okay. So in addition to that, what else do we have for my summation of forces along y direction? We have actually the normal force here to cancel out my weight, right? So we are going to have normal force here. Positive or negative again. Okay, since it's going upward, right? It is positive here. Okay, so now how many equations do we have? We have actually two equations, right? We have actually two equations here. And how many unknowns? We have two unknowns, right? So the problem is solvable here. Okay, so the idea is that you can first solve the second equation, and okay, so now we are going to number in those. And by the second equation here, we are going to have normal force equals to what? We're going to have normal force equals to 100 pound here. Okay, we're going to have the normal force equals to 100 pound here. Okay, so by the first equation, what do we have? By the first equation, we have the friction that we need. Okay, it is pretty important to note that now the friction that we solved is the friction that we need. It is not the friction, it is not the maximum friction the surface can provide. Okay, it is a friction that we need. Typically, we call it demand. Okay, it is the friction that we need equals to what? By the first equation, we're going to have it equals to 30, right? Okay, this is okay. It is pretty important to note that this is actually the friction. This is actually the friction we need. Okay. This sometimes is called demand. Okay. This is the friction that we need. And what is the maximum friction that the surface can provide? Okay, we have it here, right? We have it here, right? And the maximum friction that we can provide equals to mu s, which is the coefficient of static friction here, times the magnitude of the normal force, right? So the mu s equals to the statement of problem has already given us that, right? It equals to 0.4 here. Okay, times what is the magnitude of my normal force here? It is actually we've already solved that, right? It is actually 100, and that gives us 40, right? Okay, so typically this is okay. So this is actually the magnitude. This is actually the maximum friction that my surface can provide. It is the maximum friction that can provide. Okay, so we can call it capacity. So actually here we are going to check whether the capacity will be greater than the demand or not. In other words, whether the surface is capable to provide what? To provide enough friction, right? So here is the friction that we need. Here's the friction that we can, the maximum friction that we can provide. And what is our conclusion here? We see that the friction that we need is 30 pounds. It is smaller, right? It is smaller than the maximum friction that I can provide, which equals to 40 here. Meaning what? Meaning that my surface can provide enough friction to cancel out your external force, which means that will the object slip? No, right? No. Okay. So the box is not slippery. Okay, the box is not slippery. Okay, so this is actually our example here. Okay. So in addition to that, okay, so I'm going to give you some time to take a note and think about that here, and you can pause the video and take a note and think about that. So then we're going to talk about the second example here. Okay. Good. So now we're going to talk about the second example. Okay. Now, second example. Okay. Given. Again, I have a corner. Okay, I have a corner here. Okay. So now I have a square box here. Okay, I have a square box here. And I have an external force here applied at the very top of the box here. It is actually the magnitude is P, and it is actually going horizontally and towards the right direction. Okay. So we have the dimension of the object for each side. We have it to be 6 inch. Okay. So here same, it is a 6 inch. Same here. 6 inch. Okay. So it's the same for each side. Okay. And we have its weight equals to 100 pounds again. Okay. So the box is contacted with surface at A and B. Okay. So for the surface, the mu s here is 0.5. Okay. Now we have all the information that we need, and we are supposed to find. Okay, the magnitude of force where motion impends. Okay. Actually, we are supposed to find the magnitude of the horizontal external force such that the box just started to move. Okay. Okay. Again, how can we approach that? Okay. So again, here it is actually belonging to the topic of force analysis. And for force analysis, there are actually two steps. First step, draw free body diagram, and then second step to analyze that. And another thing is that for friction, typically we are considering the limiting state, that is when the object is starting to move but has not yet. And at that point, what should we know? We know that the friction reaches its maximum, which means that magnitude of friction equals to mu s times the corresponding normal for force here, right? Okay, knowing the 2 points, it is enough. Then we can approach that. So the first step here, okay, solution. So the first step here is draw free body diagram, right? It is to draw the free body diagram of the object. Okay, so we know that. So the free body diagram contains the object that we're going to analyze and all forces on it, right? So, and regarding what object that we're going to analyze, here we only have one object here, right? So we are going to analyze it. Draw the box here. Okay. Now we have the object. And again, we're going to include all forces on it. Okay. What forces do you think is acting on the object? First, we have the unknown external force. We have the unknown external force here, right? It is the force of our concern, right? So we have the external force here, and it's the P. Okay. In addition to that, what else should we have? We have the weight, right? Actually, it's the gravitational force here, and we know that it's going downward, and the magnitude equals to 100, right? 100. Okay. And in addition to that, what else do we have? And again, so typically for the topic of friction, the forces on free body diagram, including external force, gravity, normal forces, and friction, right? Okay, so at least we see that the object is contacted the surface at B, right? So it will have, so the surface will exert a normal force on the object at B, right? So we are going to have the normal force at B, and the direction is perpendicular to the conducting surface, right? So it is going towards R. We have the normal force here. Okay, so we denote as normal force B here. Okay, so we also going to have a friction at B, right? Okay, so now it becomes a little bit tricky here. What do you think is the direction of my friction here? Okay. What do you think is the direction of my friction here? Again, so the direction of friction is always what? It's always opposite to the motion or tendency of motion here, right? Actually, it is a relative motion between the two contacting surface, right? What do you think is the direction or the direction of relative motion between the contacting surface here? Okay. So now we are going to use our imagination here. Okay. So we have the pop box here, and we know that if we push it along the direction of the push along the direction of P, it will what? It will start to rotate, right? And once it will start to rotate here, then my B will sliding towards, my B is actually sliding towards the left, right? That means my friction is going towards right. Okay. So I'm going to do it again. Okay. So suppose that I do an analogy here, I have a bag here. Okay. Okay. Now if I'm now suppose that I'm okay. So now suppose that I'm pushing at the top point here. Then if I increase the magnitude of B such that at the point it started to move, and then the motion will be actually rotation, right? Okay, so actually it will be rotation here. And if you look at the rotation here, so the B is actually sliding towards the left, right? And then my friction is going towards right here, right? So my friction is going towards the right, and always trying to stop my relative motion, right? Or trying to eliminate trying to eliminate potential relative motion here. Okay. So what else do we have? Since the object is contacted at to the surface at A, so we're also going to have a normal force at A, right? Similar. And in addition to that, we should also have friction, right? Now, what do you think is the direction of my friction at A? Since again, if we have the object started to rotate, then my A point is sliding upward or downward here. So it will sliding downward, right? Then my friction is opposite to the direction of relative motion here. It is going towards up, right? it is going towards up here. Okay. Okay. So it is all the four forces that we have. Okay. Now we've already established now we've already have the free body diagram, and we are going to second step, establish the equation, right? Okay, second step, equations of equilibrium. Equations of equilibrium here. Okay. So now, again, how many equations do you think we have for the object here? Okay, so as in this class, we are talking about general rigid body here. So how many equations? 3 equations, right? For a 2D rigid body here, we have 3 equations. Summation of forces along x direction equals 0. Summation of forces along y direction equals 0. And summation moment about a point equals 0, right? So we're going to have, okay, 3 equations. So the first equation is summation of forces along y direction equals 0. Along x direction equals 0. Okay. So what do you think we have along x direction here? Okay. So we have the external force here, right? So we have external force here. Positive or negative. Since my external force is going towards the right, so it is a positive here, right? Okay, what else do we think? We have the friction here, right? FB. Okay, we have FB here. Again, positive or negative here. Again, it is going towards the right? So it is again positive here. Okay. Okay, so in addition to that, is that all we have? We also see that there's a normal force here going towards the left, right? So it will also need to be included here. Normal force at A, since it's going towards the left, it is negative. It is a negative here. Okay, so this is actually our first equation here. And the second equation is summation of all forces along y direction equals to 0. Okay, summation of all forces along y direction equals 0. And what do you think we have along y direction here? So we have, okay, we have the gravity, right? We have the gravity here. 100 pounds. Positive or negative? Okay, gravity going downward. So it is negative here, right? Negative here. And in addition to that, what else do we have? We have the friction here at A, right? So we have friction at A going towards up, right? So it is positive, right? And we also have the normal force at B, right? And since it's going upward, so it will also be positive here, right? Okay, and summation of forces on y direction equals to 0. Okay. Okay. So now the third equation is summation moment, right? So the third equation here is the summation moment equals to 0. Okay. Now about which point are you going to take the summation moment here? Typically, of course, you can take the summation moment here about any point. But to actually make our life easier here, we typically take the summation moment at a point about which we have a most line of action of unknown forces crossed, right? Okay, so here, for example, we can take the summation moment at A or B, right? Because both A and B we have actually 2 unknowns, the line of action of 2 unknowns cross that, right? Okay, suppose that we take the summation moment of forces at B here. Okay. And what do we have? So first we know that given that we take the summation moment at B, so both MB and FB, their line of action cross the B, right? And what should their contribution to the summation moment at B? zeros, right? Because their line of action cross that B. So the distance from a line of action of those forces to B equals to zeros. So they will not have moment about B. And in addition to that, what else do we have? Will contribute to the summation moment at B here. So we have an external force here, right? Okay, we have the external force here, and the magnitude of my the moment of my external force about B equals to the magnitude of force times what? The magnitude of force times the distance between the line of action to my point about which I'm taking summation moment, right? It is actually this distance here, and it equals to, okay. And now we're going to do some work of geometry. Okay. Given that we have the box is a squared box here, and with each side equals to 6 inch here. Okay, given that it's a 6 inch here. Okay, and then we can draw a horizontal line connecting the most left and the right vertex, and similarly draw a vertical line. And then we're going to have what? We're going to have 4 right angle triangle here, right? Okay, so now we see the total head equals to what? It is actually composed of 2 parts. It actually composed 2 equal parts, and for each length, it equals to actually, since the angle here is a 45 degrees, right? So the head equals to 6 divided by square root of 2, right? Similarly here, this height also equals to 6 divided by square root of 2. Okay, because the 2 are equal, this shape is a square, and then the total height equals to the two summation of the 2, right? It is actually 12 over the square root of 2, right? Okay, so we're gonna have the total length equals to 12 divided by square root of 2, right? And inch here. Okay. Now, positive or negative here. Okay. So since actually it's going towards, so the force here is going towards the right, then it will actually rotating clockwise or it's actually rotating clockwise or counterclockwise here. It is actually clockwise, right? Clockwise meaning that it is a negative, right? It is a negative here. Okay. It is the moment of my external force here, and in addition to that, what else should we have contributing to the summation moment at B? Okay, so we have the gravity here, but what is the contribution of my gravity to the summation moment about B? Since the line of action of my gravity crossed what? It actually crossed the point B here, right? Therefore, its moment about B equals to 0, right? Because the distance from a B to its line of action is 0, right? The line of action of my weight cross the point B. Okay, so it will not contribute to the moment of B. And in addition to that, what else do you think is contributing to the summation moment about B? We have a friction here, right? So we have a friction A here. Okay, so its moment about B equals to what? Equals to the magnitude of force here, right? Which is Fa times what? Times the distance between the line of action to actually B, right? And it equals to the length of this side here, right? It actually 6 divided by square root of 2, right? It equals to 6 divided by square root of 2. Okay. Okay. And again, positive or negative here. Since we have our pen one end fixed at the B, and another end we put it along the direction of the force. It is actually clockwise or counterclockwise here. We see that it is actually counterclockwise, meaning that it is positive here, right? It is a positive here. Okay. So we also have the normal force at A will also contribute to the moment about B, right? So it equals to the magnitude of my normal force here times what? Times the distance, again, between the line of action to A, and it equals to this side, right? It equals to the length of this side, which is actually 6 divided by square root of 2, which is actually 6 divided by square root of 2. Okay, again, positive or negative here, and it is actually counterclockwise here, right? So it is actually positive again. Okay, summation of all moments equals to 0. Okay, those are actually 3 equations that we have. Those are 3 equations that we have. Okay, so now we have 3 equations. How many unknowns do we have? Okay, let's have a look. We have 1, 2, 3, okay, 4, 5. We actually have 5 unknowns in total. So seems like the problem is not so solvable here. Okay, do we really have do we really have 5 unknowns here? No, because we are actually considering where the motion is impends, which means we know the friction here, right? We know the friction it is actually proportional to the normal force. It is actually proportional to the normal force here, right? And so the friction here is actually the maximum friction that my surface can provide. That means the magnitude of my friction equals to what? Equals to mu s times the corresponding magnitude of normal force here, right? Okay, so now actually we see that we only have how many unknowns, given that FA and FB can completely expressed by mu s, we already know, and normal force A and B we assume that, right? So there are actually 3 unknowns: magnitude of external force and 2 normal forces here. So 3 unknowns, 3 equations. Okay, now the problem is solvable here. And by solving the equation here, okay, solving the equation, we have the magnitude of the external force equals to 95 pound. This is actually the sorry, it is a 75 pound here. So in addition to that, we have the magnitude of the 2 normal forces, which are actually, so for normal force at A, it is 100 pound. So normal force at B, it is 50 pound. Okay, so now we've already solved the problem here. So it is pretty important to note here is that the reason why we can see this, the reason why we can see that the friction equals to the mu s times the corresponding normal force is because of what? Because of we are actually considering where the motion impends. Okay, it is when the motion impends. In other words, when the object has started to move, or at least it is about to move, it is at the point when it is just starting to move. Okay, it is a critical point. Okay, so at that point we know that the friction reach is maximum, and for the maximum value here, so it can be calculated by the coefficient times the magnitude of normal force here. Okay. Okay, so it is actually our class of slippery and tapering here. So if you have any question here, you can send me an email. Okay. You can send me an email or stop by my office. Okay, so actually, this is related to the last problem in our last homework here. Okay,